Hello everyone, this is video 13.2. We're going to be looking at patterns and surface area. This is probably not the best title for this section because we're not going to be talking about patterns like you might be thinking about patterns. Like when you hear pattern, you're probably thinking like 1, 3, 5, 7, 9 or something like that. And we're not really talking about that kind of pattern. And surface area is a little bit of a misnomer because although we're talking about surface area, we're not really doing a whole lot with it. We're not really calculating anything about surface area, so I don't know. It's kind of a weird name for this section, but you know what can you do? So anyway, let's get started. So I want to start this section by looking at something that we looked at the end of 13.1, and you have our five regular or platonic, whatever you want to call it, solids down at the bottom. And we talked about how these platonic solids, uh, one of the things that characterized them was that all of the boundary shapes, all of the outer surface shapes, are the same polygon. So for our cube, every one of these faces is a square. For this equilateral triangle, equilateral triangular pyramid, each one of these shapes is a equilateral triangle. These are all pentagons, these are all triangles, these are all triangles. So one of the things we could do is we could take that solid and we could cut it along some of the edges so that we could open it up and fold it out into something that's flat. And so you could see here this pyramid, if we cut along these edges going from the apex to the base, now I could take these three lateral faces and fold them out. And so this would be my base here in the middle, and then these three, 1, 2, 3, would be my lateral faces here, 1, 2, 3. And so we've folded that down. We would see then that these three edges here would be these three edges here because they were the edges that didn't get cut. So they wouldn't be cuts, they would just be folds. So we could think about taking this solid object, cutting it along a sufficient number of edges so that it'll unfold and lay flat. Now you could reverse that process and think about, you could also be given this thing down here, which is called a net, N-E-T, and I have no idea where that name comes from. So this net, you could also think about folding that up. So you could also think about going in sort of in reverse order here, like we talked about this net here. Take those three triangles on the outside, fold them up, and get that triangular pyramid there. Some of these are a little bit harder to see than others as to how they fold up. So you may see sometimes for these edges labeled. So you'll see sometimes like an A and an A. And what that means is that when you fold this together, those two A's will join back up. And so maybe they make this edge here A. And so sometimes you'll see these labeled like this. Is going to match up to this. This is going to match up to this. D to D, and then E to E. So you'll see sometimes little like almost like instructions or directions as to how this gets folded up and matched up. Um, I mean, realistically, if you were to cut this thing out and start folding it, you'd have a hard time folding it up incorrectly, knowing what shape it's supposed to make. So, but sometimes you'll see these labeled just to sort of help you out. An important thing to note about nets is that they are not unique. There's not just one way to do it. So, for example, if you were to take this square here and move it over here, it still works. I mean, this will still give you that cube, and the same thing. You could move this one up here. Now, we'll see in the next slide. That this is not always going to be the case, or not every net's going to make something, but in a lot of cases, we can move these pieces around and still get the shape that we want. So as I just mentioned, one of the things that's really interesting about having students work with nets is they'll look at it, look at the net, and after a sufficient amount of experience and work, they'll look at the shape, they'll count the number of pieces they have, and have a pretty good idea what shape it is that they're trying to make. So here we've got 4 nets, and they all 4 are using equilateral triangles. We got 4 equilateral triangles. So we know we're trying to make a triangular pyramid. But the question is, do all 3 of these work? Do all 3 of these actually make a triangular pyramid? Now we know net 2 works because we saw that on the previous slide. But does net 1 work? Does net 3 work? You could think about sort of like trying to fold this together in your mind, or actually have students work with these and actually cut them out. And that's kind of a nice thing about working with nets, is that this is naturally a very kinesthetic activity. This is not just something to look at and think about, but it's something to do. And so sometimes if you look online, you'll find patterns for nets like these, and you'll see they have these little gray pieces right here, or they'll have like little extra bits. Those little extra bits are little tabs for actually assembling these things. If you were to photocopy this, um, and maybe even blow it up to make it like a little bit larger, you could put glue or tape on those little extra tabs and use those to actually assemble these pieces. So just keep in mind that those little tabs are not technically part of the net. They're just there to help kind of put the pieces together. Um, yeah, so you can kind of look at these 4 nets and kind of get an idea of what shapes they're all going to make. All 4 of these nets will make a polygon. I'm sorry, a polyhedron. I said that wrong. Polyhedron. Another important thing from 13.2 is this idea of a cross section. So a cross section of a shape is where we take a plane and just sort of slice through that polyhedron. Um, some cross sections are a little bit more intuitive than others. We can kind of see what they're going to make right away. If we have a cube, getting a square cross section out of a cube, pretty straightforward. I mean, we're just going to cut parallel to any pair of sides, and we'll get a square out of that. Now, getting a rectangle might be a little bit harder to visualize, but it is possible. If we just take that plane and start to tilt it a little bit, so now the opposite sides are going to stay congruent, but now the other 2 sides are going to get longer because we're tilting it along that cube, and so we'll get a rectangle instead of a square out of that. But some of the other cross sections are not at all obvious. So for example, we could cut this cube and get a triangle. And so we talked about this a little bit when we talked about the semi-regular solids. We talked about the truncated cube. We used that plane to cut sort of the corner off of this cube, and you can see we get a triangle out of that. So for some students, it's really surprising because they think of a cube as being 4-sided, quote unquote. And so getting rectangles and squares are a piece of cake. But getting something like a triangle may not be obvious, but possible. Also, you could see this is a quadrilateral, but because we're cutting at this angle, we're cutting closer to the vertex here and further away from the vertex here. So, I got the wrong thing there. And so what we get then is this side here being shorter than this side here, and that's going to give me an isosceles trapezoid. Now, depending on if these 2 points are the same distance from this vertex, then it'll be isosceles because then these will be fixed, and the same thing here. So we could get a trapezoid. If we're very careful, we can get an isosceles trapezoid. But we can get a shape again that you may not anticipate. I think my favorite of these is that we get a hexagon out of a cube. This is not at all obvious to a lot of students seeing this for the first time. We've got 6 faces of my cube, and we got 6 sides of the hexagon. So this is going to hit every one of those sides to form this hexagon. If I get it rotated just right, I'll get a regular hexagon. If it's not rotated just right, I just get a hexagon. But either way, most students are not going to anticipate being able to get a hexagon out of a cube. And I think this is one of the things that's really interesting about this is getting students to think about these objects as something other than just a concrete object, but starting to think sort of abstractly about them. Um, this three-dimensional object is made up of two-dimensional objects, and a bunch of two-dimensional objects can join together to make a three-dimensional object. So once students start thinking about how this object and this object are somehow related and yet somehow different, or that these can make those or those can make these or whatever, then they're not thinking about these shapes as just this one idea over here that's not connected to anything else. They're starting to think about all these shapes and all these ideas, planar shapes, spatial shapes, whatever, is all coming together and sort of being part of a larger geometric structure. And that's really what we want students to do. Being able to look at a cube and say, that's a cube. I mean, it's a start for sure. But looking at a cube and seeing seeing the squares, seeing the rectangle, seeing the triangle, seeing the hexagons, they're all part of really getting a better idea about geometry. Now, another way that we can do this that is maybe a little bit easier for students to see, cutting a cube to get that hexagon might be a difficult trick to pull. You got to find a cube. You got to find a cube that you can cut through, and then you're also bringing in something sharp into a room full of small students. May not be the best choice. So another way to do this would be using a projection, taking a shadow of a cube. So really, to do this, all you need is a light source, and then you need a cube, obviously, and then a flat surface to project that shadow on. And if you rotate that cube the right way, you can make it so that the shadow that's projected onto the wall or the table or whatever shows that hexagon. And that hexagon that you see as the shadow is the same hexagon that you get as the cross section of that cube. So it's just another way to kind of get at this cross-sectional idea without having to actually cut things. And again, having students think about the two-dimensional properties of a three-dimensional object and vice versa. So for your checkpoint, here's 9 nets. There you go. See if they make a shape or not. And then if they do make a shape, is that shape a polyhedron? Is it not? Does it not make a shape? If it doesn't make a shape, why doesn't it make a shape? So I'll let you sort of look at these 9 nets and see what happens with them. If you have any questions about any of these nets or anything else from this section, as always, bring your questions to class and we'll get them answered. All right, thanks.